Hello, welcome to Sigma Made Simple. This week we're going to talk about sample sizes. A sample is a reasonable representation of a population that you can use to evaluate a change or a key process output variable when a change to a key process input variable in your process is made. So I'm going to click this link here and bring up this Excel file. We're going to talk about it for a little bit because pretty much anything that you need to do in statistics is going to be, you're going to be able to do it in Excel one way or another. So you don't need to spend a lot of money on Minitab and those types of things. But to calculate your sample size N up here in F1 and G1, those cells, N equals 22. So you must have three things. The Z, if you see over here in cell B2 and B and C2, the Z, that's your Z based on the confidence level. I always use 95% confidence level. That's typically what you use for statistics. So the Z would be 1.96 as you see here. The standard deviation of the population is also needed. And yeah, that means you need to look at a huge amount of data, which in the past has typically been hard to do without computers. And that's kind of why they started doing sampling in the first place. Because in the past, before computers, it may take weeks to gather the population's standard deviation because you have to get hundreds or thousands of data, as many as you can. Today, you can more than likely just pull data from a database. If not, then I recommend gathering more than 100 data at minimum, a couple hundred if you can. But a lot of it, like we're going to talk about later, depends on how much you can afford in regard to time and cost. But let's move on. The last one is their error, which is the amount of error that you're willing to accept when looking at the sample size. And that's right below the standard deviation, column C, for this example. We're going to talk a little bit more about that later on, but you get the N, which is the number of sample data needed. Here it's 22. It's up here in cell G1. So if we have a Z of 1.96, standard deviation of 29, and we're willing to accept basically 42% of our standard deviation as an error, which will get you within about 6%. It gets you pretty close. That's what I usually use. 12.32. So the formula for this is right here. And I'm going to show you the easier way of looking at that. Hold on a second. So this is your formula. You take the Z times your standard deviation. You divide that by the error, and you take that result squared. And that's going to basically you round it up to the nearest whole number. That's going to give you your sample size. Here, like I said, it's 22. So, like I said here, I'm using a percentage of the standard deviation. You may not want to do that. You can talk to your statistics people. If you do this way, though, with 42% of your standard deviation, since your range is 6 times your standard deviation, you're looking at basically 1/6 of 42%, which is like 7% or something like that. I remember the exact number. But what we're going to do here is we're going to change some of these things. I'm going to change the error just so you see what happens to the 22 here. I'm going to change the error to a 10. And then you can see if I'm willing to accept 10 points in error, which is less than what we had before, my N value goes up. Now, if I'm willing to go to 15, if I'm willing to expand my error, my amount that I can be off, then it gets reduced to 15. And so this is a lot of people have problems deciding on the error and calculating the standard deviation. But do your best. You can tell later on how things are going. I'll show you another trick afterwards. So if you want to get this Excel file, go ahead and email me at sigmamadesimple@gmail.com and I'll send it to you. You can just plop your numbers in here. You really only need to put the standard deviation in there and it'll automatically do 42%. You can change it if you want. It'll tell you what your sample size is. Now we're going to play around with this a little bit more. Now note how changing the standard deviation changes the n. Okay, now I'm going to change the standard deviation. I'm going to just remove it, take it down by 4. Now I'm not going to change, actually, first I'm going to take this and 42% because I'm always going to keep 42% because I want that to be consistent. So let's take this down to 24. See, um, because my error and my standard is a percentage of my standard deviation, my n doesn't really change. Okay, now let's take it to 29. Basically, it's the same. So realistically, your n is very much related to the percentage your error is in your standard deviation. I'll take that back to 24. Oh, actually 34. We had 29 in here before. So there we go. So I'll take it back to what it was before. Let's just make this a solid error. Let's change the error. And then, of course, if you're changing your standard deviation, you're changing the proportions, so they're going to change. So that's just something interesting I thought you might like to see, is how that kind of changes. The last thing you can change is your, if you look down here, always use 1.96. If you look at D or row 10, underline D, this green area, it says always use 1.96 for your Z. That's a 95% confidence level. Now, if you want to go to a higher level, like a 99% confidence level, you can put in there 2.57. And then you have to collect, of course, more samples. And then you go down to 90% confidence level. I don't recommend that. You go to 1.64, and then you can see there's fewer samples because you're only 90% confidence. So that's kind of how it works. You know how to calculate it now. We're going to move on, talk about some other things. It's a little bit of advice. You should use as big a sample size as possible. Even if your N is high when you calculate it in Excel, and if you can collect more samples, you should, okay? Because it's just going to make it more, it's going to make it more accurate. Because even though a sample size is meant to represent the population, um, there's always going to be some sort of chance for error. So higher the sample size, the better off you are. So even though sampling is an easier way to gather a small representation of the population, it's not always accurate. So remember, the more samples used, the less likely you are to have an error. So I would use whatever's in the Excel file as your minimum. If you can collect more, great. If you can do 100, if it doesn't take too long and it's not too costly, then collect 100, maybe 200. I've even used 1,000. If it's expensive or it takes a long time to gather the sample data, use the formula in Excel I showed you earlier. I recommend you always collect at least 22 data, even if the N in Excel formula is lower. It's up to you to balance the cost and your time. The biggest thing is just to realize the higher your sample size, the more accurate it's going to be. So in some cases, like admissions to a facility, you're not going to be able to collect the data because every month you're going to get a number. And when you look at the past data, when you look at your past data, you're going to need to look out for multi-frequencies and changing trends. You must have a monofrequency and account for changing trends. If this is a new idea to you, watch the video linked in the description called Norma Data is Not Always Usable. There's a video in the description here, and you can watch that to understand that better. Um, Many times I prefer not to do sampling at all, actually. I use control charts, mostly individuals charts. They're just as accurate as sampling and I tend to be quicker. I just look at trends in the data and where the data fits in 6 buckets of your range. There's a video linked in the description named Improve the Process Quick, and it talks about the relationship between histograms and eye charts and how powerful the eye charts can be and how quickly they can give you a result. There are other ways. We'll talk about those in later videos. So sampling is a reasonable representation of the population used to speed up the process of identifying changes in your processes. You use as big a sample size as you can afford as far as cost of time and money goes. And sampling is not always possible. So you might want to look at control charts. That's the control phase of the DMAIC process. Um, if you're unfamiliar with that, I suggest you go back to the earlier videos and start watching from the first one all the way through. So is the difference in the mean and two sets of data statistically significant? That's going to be in the next video. If you found this video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find the video useful, then subscribe in the hope that upcoming videos will be. Eventually, we're going to go through projects using Lean Sigma, Six Sigma tools, as well as the tools needed to support them. Remember, a wise person learns from their mistakes, while a genius learns from mistakes of others. And, in this case, with collecting sample sizes, don't create a monster bigger than the one you're trying to slay. So until the next video, keep your data clean and take care.